All right, Chapter 5, Section 5, Permutations and Combinations. Two very large words that describe a fairly simple concept, counting. Okay, and I bring this up because when I was in college, we had a graduate level course called combinatorics that dealt with permutations and combinations, and it was simply and deceivingly described in the student handbook as a class on how to count. So several of us, myself included, joined that class under the idea of like, oh, we get to do this very, very simple concept of counting, which is literally like the first thing you learn how to do in your lifetime regarding mathematics, is how to count things. However, the fact that it was a graduate level math course should have tipped us off that this was a little bit more difficult than, say, counting the number of apples you see on the teacher's desk. Okay, this is a little bit more complicated. Now, in this section, in regards to what we will be doing in this class, obviously, I'm not going to be having you do graduate level collegiate work in a math class. We're simply going to be scratching the surface here and talking about what permutations are, what combinations are, and why they apply under this unit of probability, of discovering likelihood of an event. In its most general sense, why is being able to count useful for probability? I will reference this back to Section 1. In Section 1, we talked about a term called sample space. And when in regards to sample space tells us the realm of possibility of an event happening, okay? And in Section 1, we dealt with some very, very familiar, very simple types of sample spaces. For instance, flipping a coin. The sample space there, flipping heads or flipping tails. Two possible outcomes in that of those events, right? That is a very, very simple form of counting. 1, 2, done. A die, rolling a die, has a sample space of 6. 1, 2, 3, 4, 5, and 6, each side, its own number. A deck of cards, the other set of examples that we've done throughout this unit. A deck of cards, a standard deck of playing cards, has 52 cards in its sample space, 52 possible selections. There are other familiar ones that we have in our own life that, if I were to tell you, say, like randomly select a day of the week, the sample space there would be 7 different options: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Okay. If I were to say randomly selecting a month of the year, that sample space would be 12 large, one for each month. Okay, to use some calendar options. Another familiar one would be me saying something about selecting from, say, the letters of the alphabet, A through Z. There are 26 letters in our alphabet. That sample size would be 26 large. All right. In each of those cases, those are just things that we're very familiar with. Things can obviously get far more complicated. Okay. And that's what this section is going to be about counting those sample spaces. Okay. So bringing it back to permutation and combination, ultimately what we're going to be doing is discovering the size of sample spaces that can then be applied as the denominator in our probability. Okay, for instance, if I was trying to find the probability of me selecting out of all the letters of the alphabet, randomly selecting somehow a vowel. There are 5 vowels, A, E, I, O, U, out of 26 letters in the alphabet. That'd be a 5/26 probability. If our sample space gets more complicated and much larger, here's where we're going to be using permutation and combination. Okay, so what is the difference, the fundamental difference between a permutation and a combination? Ultimately, both of these things deal with arrangements of objects. Arrangements of objects. And these objects can be anything. And most familiarly with us, those objects come in the form of like letters and or numbers or characters on a keyboard. Okay. And so in regards to a permutation, looking at this formal definition, is the arrangement of objects in which the order matters. And this phrase right here is worth highlighting, underlining, putting in a different color, whatever you need to do to draw attention to it. Because this is the main distinction for what a permutation is. Order will matter. Now, it also stands to reason, this is a spoiler alert, we're going to be looking into this tomorrow with day 2 of this set of notes, but for combinations, order will simply not matter. Okay, and I'll go through more examples of combinations tomorrow, but here are some examples of things that involve permutations. License plates. The order definitely matters. License plates. Many of us are in some way, shape, or form at least familiar with someone's license plate in our family, just because we're used to seeing all these cars out in the world. And so being able to identify our license plate is a quick way to say like, oh, that's my ride. Okay. Many of us in some way, shape, or form at least know something about like a family member's license plate, even if you know the whole thing. Okay. Some are a little bit more recognizable than others. People can actually create words and phrases and stuff, but we're talking about just generic license plates and different ways to arrange it. Okay. If you were to jumble up the letters and numbers in your family's license plate, it has just been created into a new, different, unique license plate. Okay. For instance, if a license plate began A, B, yada, 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 and then you had another license plate that everything else was the same, but you simply swapped those first two letters to make it BA, that is a completely different license plate. Another set of permutations that's familiar to us, lock combinations. For those that have been to the high school or have had a locker or some sort of lock before, you will be very familiar with your own 3-number combination to your lock. Now, the combo for that lock, please do not confuse that with the combinations that we're going to be talking about tomorrow. This is its own thing. In fact, this is a permutation to be more accurate here. So your lock permutation, so think of it this way. If you and your best friend happen to have the exact same numbers on your lock combos, okay, but your numbers were in different orders, all of us have done this before in some way, shape, or form. If we've tried to undo like our own lock combo and we accidentally mixed up 2 of the numbers, it will not unlock. Okay. Just having the correct numbers is not enough. I have to put them in the correct order. Okay. Another case that I haven't listed here, but that's more than familiar to us, passwords. Okay. The password to get into your own email address, into your own accounts and subscriptions and stuff like that. Your password is unique to you, right? And you've likely chosen something that has some meaning to you and some sort of initials and combinations of numbers or dates or whatever it might be. Okay. And if someone were to blindly guess that information, but mix up the letters and or numbers, they would fundamentally be giving a different password and they would not be able to get in, because these permutations, the order matters. Those are examples of permutable or permutation types of arrangements. So how will that be applied? Okay. Before I get too deep into our examples, I first want to introduce us to a new formula. And don't fret, you don't have to memorize this formula, because as long as you write it down, you don't have to memorize it. You get your notes on the final. But we see this new formula, NPR. And for those that have spent way too much time looking at your own scientific calculators, you may recognize this phrase. Okay, just to quickly show you, on my standard scientific calculator, okay, the NPR function is this little yellow function above my 1 button. And next to it, you'll notice NCR. P stands for permutation. C stands for combination, right? And that's the one we're going to be dealing with tomorrow. But there is an actual function on your scientific calculator that will perform these permutation formulas. So there's the good news. There's actually a calculator button that will take care of this. And this scientific calculator, whether it be through Google or through Big Ideas or your own personal scientific calculator, this can be solved in a calculator, and I will encourage you to do so. Okay, so they'll actually be pretty quick calculations from that standpoint. But what does the actual function do? It does this mess. And here's where we're going to introduce a new math operation. You will notice some exclamation points here. No, this is not a very, very exciting math formula, and that's why there are exclamation points. No, that's not the case. This actually is a math function. And over here in the margin, I've described it. What does the exclamation point mean? It's what we call a factorial in mathematics. Maybe you happen to be familiar with it. If not, that's totally okay. This is what a factorial does. It's basically a countdown of a given number. So if I were to say do 3 exclamation point or 3 factorial or say 5 factorial, it's basically a countdown starting at that number where I'm multiplying all those numbers together. For instance, 3 factorial would be 3, 2, 1, where I multiply 3 times 2 times 1. 5 factorial would be 5, 4, 3, 2, 1, but I'd multiply 5 times 4 times 3 times 2 times 1. So actually at its core level, this is not a new math operation. It's just multiplication, or rather string multiplication, but it's a countdown set of string multiplication. And I'll go into why we do this countdown string multiplication in our first example. But for right now, this is technically what's happening with that formula, right? So in a permutation, we're taking n and r right here and using that to solve our factorials. Okay, so what do n and r stand for? N is going to represent the total number of objects that I'm selecting from. Okay, and that will make more sense as we get into these examples. So let me use the example right now of just saying like picking 4 letters out of the alphabet. Picking 4 letters out of the total alphabet. So for total objects, those would be the total possible number of letters I could select from. In this case, 26 letters are on our English alphabet. Okay, so n would be 26, both in this notation right here and in the formula. N would be 26. R represents how many objects I'm selecting from that bunch. So if I said I'm picking 4 letters from the alphabet, n would be the 26 total letters in that alphabet, and r would be the 4 that I would be picking out. Again, 4 going in this notation right here, so it would read 26p4. And then in the formula, it'd be 26 factorial over 26 minus 4 factorial. Again, those numbers kind of depend on the situation we're dealing with. Okay, so without going into too much detail right there, now let me just get into our examples so we can actually see how to apply this and use our calculator ultimately, because what you will very likely appreciate is that when it comes to the calculator work here, it's just really a handful of button pushes and it will give you the answer on the other end. So the first thing I'll do is I'll slog through a little bit of where it comes from and why it does what it does, and then I'll show you how the calculator gets applied here. Okay, so let's look at our first example. And this will be the only example that we do today. We'll do 2 pieces of this example. And then tomorrow we'll do 1 more example of a permutation just to kind of get a little recall. Then I'll talk about combinations and do an example with that, in which the order won't matter. But again, that'll be tomorrow. So for our 1 example today, this is our first several problems in this section are going to be dealing with this kind of scenario. You're going to be given a word, maybe a familiar word, like flowers in this case. And you're going to be asked this question. Find the number of ways that you can arrange, or in this case, rearrange, all the letters of a given word, in this case, flowers, right? And so for part A, we're going to be rearranging all the letters of the word. So it might come in useful to know how many letters there are, right? I'm not going to be magically inputting new letters. It's just going to be the letters that exist in this word as they are. Okay, for part B, now instead of rearranging all the letters, I'm going to be rearranging simply 2 of them. So I'm going to be taking 2 out of this word and creating different permutations of those 2 letters. Okay, so ultimately, what is important to understand here is, why is this a set of permutations? Because the way that these letters are arranged right now is familiar to us. This actually makes a readable word, flowers. Okay, there is a meaning to that word. If I were to say, I don't know, take this S and move it up into the front, it would now say flower, right? Okay, and it's now gibberish, right? But that rearrangement, moving the S to the front, has just created a new word, a new spelling. It would be how we would, the arrangement of letters or the spelling of a word does in fact matter. And so anytime any one of these words gets rearranged into somewhere else, wherever that may be, you have just created a new word, whether or not that word is readable or not. And so in this case, order matters. Because again, the way I read a word is going to matter about whether that word actually has meaning. Okay. And even for part B here, when I rearrange 2 of the letters, say like F and L, let me just take the first 2 out. If I were to have the two letters FL or LF, those are two different arrangements. Okay. And so when I'm talking about arrangements of the letters where the order matters, FL would be distinct and unique from LF, just like a lock combo, right? If you were to have the numbers 5, 51, and 90, 5, 51, 90 is one arrangement that might unlock one lock. But then if I were to do 51, 5, 90, that would not unlock the same lock. Okay, so let's do these two examples. I'll first show you kind of the long way about how to apply this formula and kind of where it comes from. And then I will show you how to quickly do it on a calculator. Okay, so in this case, we are given this word, a familiar word, a nice word that you should get your mom on Mother's Day. And heck, get it for your dad on Father's Day. Surprising. Anyway, so flowers, right? The first thing that's probably worth noting here is how many different objects there are in this phrase. In this case, there are 7 different unique letters. And that term unique actually matters here. Right now, you're not going to get thrown many curveballs here in this section. But say, for instance, I'd be given a word with 2 R's, for instance, that makes things a little bit more complicated because me having 2 R's, even though they're each distinct R's, if they were ever like pushed together, RR would be the same thing even if I swapped them as RR. Get what I'm saying? So that's more of like an advanced set of combinatorics for like a college class and stuff like that, is dealing with repeated objects. But again, neither here nor there, because we're going to deal with stuff where they're distinct, unique letters, like here. In this case, I have 7 individual letters. Unique letters, rather. Okay, so one way to kind of think of this from a abstract sense is I have 7 different positions that I could like slot each one of these letters, and then flowers is one of those arrangements. F L O W E R S. Right? If I were to arrange them that way, that would be one of the possible arrangements of those letters. It happens to make a spelled readable word, flowers. Okay, but here, let me just kind of describe where the factorial and where it gets applied to a permutation, where that comes from. So for my first position here, let's think about how many options I have to put in this position. Okay, any one of these 7 letters can go there, so there are technically 7 options that can go in that first position. Well, once I have selected one of those letters, there's going to be so many that are left over. Okay, so let's say I chose F. After F has been taken, there are only 6 more options that remain after that. Okay, and what I'm going to end up doing with these numbers is I'm going to be multiplying them. Why? Okay, so I had 7 options here. Let's say I happen to put an F here. I could have FL, FO, FW, FE, FR, FS. That's 6 different options for that F. Well, then what if I had an L here? I could have LF, LO, LW, LE, LR, LS. There's another 6 options for L. And as you can see, is I can do that with each of the 7 letters. But in each of those cases, there are only 6 other options for place number 2. Okay? And here's where it follows. So let's just kind of continue with the string. Well, if I had 7 options for position number 1 here, and then I'd only have 6 other options for position number 2, there would only be 5 remaining after 2 of them were gone. There would only be 4 remaining after those 3 were gone. There'd only be 3 remaining, and 2 remaining, and 1 remaining. And what we start to see is here's where we get that countdown multiplication. This is where factorial comes from. It comes from this concept of counting, combinatorics. In this case, what we would call a permutation. And so it's one thing to have to write this out for, say, 7 characters, but what if I gave you something like the full alphabet and it was 26 characters? It would be very annoying to write 26 times 25 times 24 times 23 all the way down through 1. And so lazy mathematicians came up with a way to abbreviate that. They're like, factorial. They're like, oh, I'm going to multiply all the numbers after that. Oh my gosh. Okay, that's a stupid joke. Anyway, so the factorial, the exclamation point, that's what it stands for. 7 times 6 times 5 times 4 times 3 times 2 times 1. Obviously, this is a much shorter way to write all of that. So that's where the factorial comes from. And if I were to do this on a calculator, 7 times 6 would give me 42, times 5 would give me 210, times 4 would be 840, times 3 would be 3,360, times 2 would give me 5,040, times 1 gives me 5,040 again. Okay, don't feel like you have to do that stuff in your head. Don't even feel like you have to do this all on a calculator because, again, that factorial is an actual operation on your calculator. Let me show you how to do that right now. Okay, so let me zoom in a little bit here. Okay, so one thing I want to point out, and again, all of your scientific calculators will have this as well. Above my 3 button, you'll notice this little X exclamation point. That exclamation point is our now famous factorial. And so how would I do this on a calculator? In order to do a factorial on a calculator, what I'm going to do is I'm going to first put in the number that I'm taking the factorial of. So in this case, 7. And then mine was a secondary function, this thing in yellow above here. Just be careful about what calculator you're using, whether it's on Google or Big Ideas or your own scientific calculator. In my case, it's a secondary function. So I have to use the shift button and it does the full multiplication in just that series of buttons, 5,040. So what is 7 factorial? 5,040. What does this number tell me? What is the significance of this number? This is the number of different ways I can rearrange those letters. 5,040. That's a lot of ways. That's a very different sample space than, say, figuring out how many different ways I could roll a die or even 2 dice. Okay, a much larger sample space. And that's why just simply rearranging this and trying to write them all down on a piece of paper, definitely not realistic. 5,000 plus different ways to rearrange these letters. And how would this be applied to probability? Let's say I had 7 different ping pong balls with each of these letters written on them. And I stuffed them in some like bag or something like that you couldn't see them. And I was like, okay, in this bag, you're going to randomly pick out these balls blindly. And in whatever order you select them in, we're going to write that word. What would be the probability that you'd come up with the word flowers? Well, there's only one way to arrange those letters in the way that makes this word flowers. So that would be exactly one way. Out of how many possible ways to arrange those letters? 5,040. If you were blindingly picking these letters out of a bag, there would be a 1 in 5,040 chance of you actually spelling the word flowers. That's how this could be applied to probability. Okay, well, that's where factorial comes from. Now let me describe how we use the actual formula. So in our notes, we were introduced to this math operation, NPR. NPR did the following. It took n, again, n represents the total number of objects being selected from, and it put it over, in a fraction form, this difference, again, total number of objects, subtracting out how many objects I'm actually selecting from that, and again, doing a factorial. This is the formula. Again, I'm going to show you how to do this function on the calculator itself. But in this case, let's actually apply this example. So the P stands for permutation right here. So it actually stands to reason that tomorrow when we get into combinations, this will be the letter C instead. N represents how many total objects are being selected from. In this case, I'm rearranging the letters of this word. There's 7 unique objects here that are going to be rearranged. So N represents these 7 possibilities, FLOWERS. R represents how many objects I'm actually rearranging, or how many I'm selecting. In this case, since I'm rearranging all the letters, all 7 are also there. Okay, so now when I plug it into this formula, on the numerator, n is 7, So that's 7 factorial, also as 7 times 6 times 5 times 4 times 3 times 2 times 1. Don't try to do that in your head. Okay. In the denominator, I have 7 is n still. I'm subtracting out r. Well, r is still 7, and that's going to be taking the factorial right there. So in this case, this is going to reduce to be 7 factorial over 0 factorial. Again, don't fret right here. This is not something you're going to be expected to do every time because, again, there is a math calculator function for this. Okay. And you may be thinking like, oh, this must be 0. Actually, interesting fact, if you were to attempt 0 factorial on your calculator, here's what happens. So again, my factorial button is this secondary function above my 3. If I were to do the number 0 and then do factorial 1. 0 factorial is 1, meaning this denominator here is 1, meaning that 7 factorial, whatever that value is, over 1 is still just 7 factorial, which is what we got with our last problem. But here, now let me show you how to use the NPR function. All right, so 7p7. Here's how you would do this on a calculator. Let me zoom in again on our calculator so that you can see what's going on. Many of you that have way too much time on your hands and have looked really closely at these calculators may recognize this phrase, NPR. NPR represents our permutation formula. This is the button, the function that we're going to be using on our calculator. Again, mine is a secondary function, so I'm going to be using the shift button. And next to it, you'll notice the NCR, which we'll deal with tomorrow for combinations. So that will be the number I use. So how do I actually use this in my calculator? So in order to do this 7p7 NPR, I'm going to start with my n value, 7. Now I'm going to tell the calculator to use that NPR function, that secondary function. So I need to use shift and then the NPR. It'll be a different possibility on your own scientific calculator, on Big Ideas, or on Google Classroom or Google Calculators, those sorts of things. So just be aware of that. But now what it's going to wait for is like, okay, now what's the R value? Well, in this case, it happens to be 7 again, so I could type in 7 again. And now when I hit equals, hey, there's a familiar number, 5,040. So again, just off a series of buttons, I found out that in this case, 7p7 is equal to 5,040. What does that 5,040 represent? It's the number of ways that I can rearrange 7 objects, 7 distinct objects, into 7 new places. Okay, 5,040 ways for me to rearrange the letters of the word flowers in this case. All right, great. Well, now let's apply. Let's do example part B. All right, so this is a very, very similarly done problem, except now there's a fundamental difference. In this case, now I'm only rearranging 2 of the letters of this word. So if you want to think about it this way, I now have just 2 slots. And in this case, if we want to think about it the long way here, I guess it's not too much longer now. How many options do I have for my first slot? It's still the same 7 letters. And I'm going to multiply that by, once I've selected one of the letters for the slot, how many letters are left over, because I can't have like FF because there is no second F, right? So I have 7 options for position 1. There will be 6 remaining for position 2, and that's it. In this case, it equals 42. Okay, but let me, again, it happens to be simple enough just to solve it this way. There are, in fact, 42 ways to rearrange 2 letters of this word. But let me, again, apply our permutation formula because it will come in handy when these numbers get a little weirder. In this case, it's simple enough. Our numbers are not particularly huge, but let's apply our NPR again. All right, so NPR, again, gives us this formula. We just have to be able to establish what is N, what is R. This is something I can do on a calculator. Again, this is the long way. I'll show you what happens here in this case. But N and R, now that I'm only selecting 2 of the letters, my N is still the total number of objects. There are still 7 distinct letters. R in this case now is changing because unlike the last example, I'm not rearranging all of the letters. I'm only rearranging 2. So R is the 2 selections that I'll be making. So in my formula, n is still 7, so I'd have 7 factorial, which we now know comes out to 5,040. In the denominator, I'm now going to have that 7 minus r. Instead of r being the same thing, it's now 2 and taking the factorial. So what happens here? This becomes 7 factorial over 5 factorial. Now, from a long mathematical sense, and the reason I'm doing this is because this is the stuff that I had to do when I was in high school, so you're welcome that you don't have to do this. What I would have to do here is I'd have to rewrite out 7 factorial as 7 times 6 times 5 times 4 times 3 times 2 times 1. It's a mouthful. In the denominator, 5 factorial would be 5 times 4 times 3 times 2 times 1. But let's see what happens here. I have one long string multiplication on top, one long string multiplication on bottom. Look what happens with the 5s. They cancel. The 4s cancel. The 3s cancel. The 2s cancel. The 1s cancel. Look what I'm left over with. Just in the numerator, 7 times 6. Sound familiar? 7 times 6 is the 42 possible ways that I can rearrange these letters. But now let me again get back to how to do this on a calculator, because again, these numbers are friendly enough, but it will come in handy, I promise you, on how to do this on a calculator. So again, in order to do this NPR on the calculator, I'm going to start with my n value. So I'd start with 7 in this case. NPR, again, for me is a secondary function above my 1 button. So I have to do Shift 1, which again is that's the NPR button. It'll be somewhere else on whatever calculator you use, maybe. But now it's waiting for my R value. In this case, asking me how many of this 7 are you selecting? In this case, I'm selecting 2. So I put in the 2, hit equals now, 42. Those were several different ways on how to get our final answer. But again, our punchline here, of the 7 total objects I'm selecting from, the letters in the word flowers, I'm picking 2 of those values. In the calculator, when I did it, it came out with the number 42. That means that there are 42 ways that I can rearrange the 2 of the letters of the word flowers. Okay, if you wanted to list them out, some of them would be like FL, which is different than LF, or I could do RS and then SR. Okay, I'll let you play around with that stuff. But in any case, we end up with 42 unique ways to rearrange 2 of those letters. And so for tomorrow's notes, we'll do one more example on permutation just to get that kind of recalled back into our minds. And then we'll wrap that up, wrap up this lesson, this last lesson of the semester, by talking about combinations in which the order does not matter. Okay, but that will be tomorrow. So let me go ahead and stop recording now.